The past two lectures, we talked a lot about how the molecules move, how the molecule move inside the stationary phase or through the column, and then what's the job of the mobile phase and how the setup looks like, where we place our sample mixture, and we talked a bit about the retention time and so on. And almost two lectures I stressed a lot on how the molecules move, especially from the point of view of adsorption, desorption, and how the mobile phase helps to push your molecules or your sample from the column inlet to the column exit, and in between whatever happens inside the column is something governed by a series of operations. Yeah, so we talked only in terms of adsorption, desorption, and somewhere we mentioned about the solubility of these compounds in the mobile phase and so on. Obviously you can learn chromatography in a very simplest possible way. I can say it in 5 minutes, like a column chromatography, how the setup looks like. You add something at the inlet and then you throw some solvent in. For some good reasons it's going to separate the molecules, and that's the end of the job. We can all stay happy. But we talked a lot because we are going to study a bit about theory, and we have to. And why do we care that where the molecules move inside the stationary phase? And that's because we are interested in the outcome, experimental outcome of the column chromatography. For example, if you because just imagine, I know you are in the final year and you might have studied a lot of chemical processes, like you take a reactor and then you add, say, some reactant A. Oh, I couldn't see the color. Something is happening. So let's assume we have some reactor. Let's add a reactant A, and then let's assume we add say some reactant B, and let's say A plus B, they combine to form C, something like 1 mole of A, 1 mole of B, 1 mole of C. So if you put a UV spectrophotometer, for example, in this type of reaction, and then if you and just assume this UV spectrophotometer can measure the concentration of A and also the concentration of C, which is your product. You must be used to this type of chemical reactions in many of your modules which you are studying, especially in the last 3 to 4 years. So in this case, if you look at the experimental outcome, if you plot the time versus concentration of A and concentration of C, concentration of A, say if you start from 100 grams per liter, it's going to decrease with respect to time. So this is some concentration at any instant of time. So at any instant of time, you have one unique value for your concentration. So when time t equal to 0, your unique value for concentration is 100 grams per liter. And if you plot the product concentration at time t equal to 0, it's going to be 0, and then it will eventually increase with respect to time. Say at particular some time, your product concentration will be one unique number, one specific number. So this is your experimental outcome. So if you plot the experimental outcome in terms of concentration, like concentration of your reactant, which is Ca, and then concentration of your product, you get some unique number at any instant of time. And if you look at the curve, it more or less it's follow an exponential trend. And normally we use something like a first order kinetics or second order kinetics. You must have studied this for sure. You should know what is this first order and second order. But so this is not the case when you are dealing with chromatography. When you are performing an experiment using a column chromatography, when you place our sample in the inlet, so let's assume for some reason let's assume we have like a UV spectrophotometer or any detector here that measures your concentration, say time t equal to 0, say one big value. So let's assume this is concentration of A. So let's assume whatever the sample that we place here, that's sample A. So that's concentration of A, let's say 100 grams per liter, or if you want we can express say 100 molecules for example instead of grams per liter. But once you pass your mobile phase at the exit of your column, you won't get something like one unique concentration. Say like I get 100 grams per liter at the column exit, assuming there is no chemical reaction happening inside the column, but rather we get a distribution. We get a distribution, something like a Gaussian distribution. I explained you in the previous lecture why we have a Gaussian distribution. So, and this happens, that's because so many events are happening inside the stationary phase. One is I talked a bit about adsorption, and that controls your retention time of your molecules, and also I said something about this molecular diffusion, and also if you have some concentration plug, it will diffuse to the right side and it will diffuse to the left hand side if this is your solute molecules. So if you don't understand, please watch the previous lecture. And your experimental outcome is always a distribution. Mostly it will be like a Gaussian distribution. If your experimental outcome is one unique number, say 100 grams per liter, we don't have to discuss all those things about adsorption factor, desorption factor, what the retention time is all about, and what is an equilibrium constant, and so on. And that's why we are going a bit slow, because probably this is the first unit operation where you are seeing or where you are observing the outcome of your experiment, which looks like a distribution rather than a specific unique number. Yeah? So that's why we have to deal with this process in a slightly different manner. We have to know where the molecules move. Obviously we cannot track the molecular movement, but we can propose the theories, so something like based on the knowledge of what is a mass transfer, what's an adsorption, what's a desorption, and what can drive adsorption, what can drive desorption, and so on. In fact, there are few other reasons that we can, few other concepts that we can think of in order to explain why our experimental outcome from the column chromatography experiment have a Gaussian distribution. So that's what we are going to cover in this lecture. So some of you might think like we are going maybe over too slow, in fact, but it is okay, because this is not an easy topic to explain. Just to say like something goes in, 100 grams per liter goes in, there is no chemical reaction, no evaporation, so that I can expect 100 grams per liter at the column exit. Obviously we get 100 grams per liter, but it will be distributed. So that's the whole idea of these things. I think so far all is okay, and I hope you all know what is a Gaussian distribution is. Yeah? So before going to theory, I will just quickly show you, we can talk a bit about this Gaussian distribution. Say like 1 2 3 4 5, let's say we have 10 molecules at the inlet, and then it travels through the stationary phase, and then I already said what's the reason why we get a distribution. Try to watch it. So say at some time, say T1 we get 1 molecule, T2 we get 2 molecules, and T3 we get, sorry, T2 we get 2 molecules, T3 we get 3 molecules, and then again at when time t equal to T4 we get 2 more molecules. So how much we have now? 5 6 7 8, and then when t is equal to T5, let's say we get 2 more molecules, and t equal to T6, let's say we get 1 molecule, something like that. Yeah? So if you plot this one, you will get something like a Gaussian distribution. So what is this Gaussian distribution is all about? So you will have a peak maximum, so that will be nothing but your mean concentration. That will be mean concentration. If you take the area under the curve, that should represent whatever that goes inside your column. So whatever the area under the curve, that should be equal to 100 grams per liter. So I hope you all used this UV spectrophotometer. Yeah, so you know all how to generate a standard plot. So what we do is like we mix, say like 10 grams per liter, 20 grams per liter, 30 grams per liter, 40 grams per liter, 50 grams per liter. So we take some solute, we add 10 grams to 1 liter of our solvent, and then we go to UV spectrophotometer, we check the absorbance units. So say like 0.1, 0.2, 0.3, 0.4, and we get something like a curve. So what does that say is like if my absorbance is 0.2 from the UV spectrophotometer, my concentration will be somewhere around 30 grams per liter. But when we are using a column chromatography, what we do is like we inject pure compound of A, say like say some 10 grams per liter, something like that. Let's assume we injected 2 ml, and then whatever the distribution that we get at the outside, we take a area under this curve, and we make that area under the curve will be equal to 100 grams per liter. So something like you plot area under the curve on the x-axis, and then you plot your concentration under the y-axis. So we make a standard plot like that. So when we are going to use column chromatography, if you want to know the concentration of the species, so this is the plot that we need. Anyway, you don't have to worry about these things. I showed this particular concept just to show that you won't get a unique peak in the column exit, something like just follow the highlighter. You won't get a unique peak at the column exit, something like this. Rather, you will get a distribution. So if you want to quantify what's the concentration that should correspond to the distribution, you should take the area under the whole curve, and we can assume that whatever the area under the curve, that should be equal to some specific concentration units, something that we can express in terms of grams per liter. It's defines some values or some terminologies. Let's call it as maybe retention factor, maybe. The first two lectures I said to you like different molecules spend different amount of time traveling through the column, and whatever the amount of time spent by the molecule from the moment you inject to the column at the column inlet, and at the moment it comes out of the column at the column exit, that we can monitor using some detector. So that's nothing but your retention time. And I already said that the molecules, your analyte molecules, is retained inside the column, and also how do you call, like your molecules are distributed between the solid phase and also in the mobile phase. So that's why you have that equilibrium constant K. If you remember, we talked about this in the previous lectures. So stationary phase and mobile phase. I even said if the K value is higher, then the retention time will be higher. If the K value is lower, then the retention time will be lower. So the whole purpose is like is to understand that whatever or the time spent by the molecule inside the column, that involves two different factors. So which means the molecules spend their time in two places inside the column. So one is in mobile phase It spends some time in the mobile phase, and it also spends some time in the stationary phase. So if you remember those diagram, so you something get adsorbed and then it will be knocked back by the fresh solvent, dissolved, go to the next active site, and then it will be dissolved by the mobile phase. So mobile phase will carry again this particular molecule, just to follow the pen, goes to the next site, and then again the fresh solvent or the mobile phase will knock this adsorbed molecule and then put it, transfer it to the next active sites, and so on, and eventually it reach the column exit. So the retention time is dictated by the time spent by the molecule in the mobile phase and also in the stationary phase. So we can give it, or if you want we can write it in a mathematical way. So let's call TR as our retention time. That will be equal to the retention time of your analyte in the mobile phase, let's call it as Tm, plus the retention time of your analyte in the stationary phase, let's call it as Ts. If you want you can give some equation number. So what we do, like this type of, so we can get these values. It's very easy to get the value of TR by performing an experiment. This can be experimentally determined. Experimentally determined. So what is this TR value is about? TR value is something like so TR value is, imagine you have, let's assume you have only one single molecule for the moment. That will make it will be easier to understand if you assume that way. So this is our analyte A, and then let's say this is our mobile phase. We are supplying our mobile phase. It can be any solvent or a solvent mixture, and let's assume analyte A, okay, it's soluble in mobile phase. This is a must rule. And then analyte A, it also interacts with our silica particles, which is nothing but our packing material in the column. So just assume everything is packed with silica particles. Okay, better I put few more molecules because I want to show the Gaussian distribution. So let's assume we have 6 molecules, and obviously it will travel through the column, and then I said we always have a Gaussian distribution, say like 1 2 3, and then let's say 2 more molecules, that makes 5, and say 1 more molecule here. So this is roughly a Gaussian distribution. So at time t1 we get 1 molecule, time t2 we get 3 molecules, time t3 we get 1, and time t4 we get 2 molecules. So this is roughly a Gaussian distribution. Yeah. So what we call it as a retention time is the time taken by the molecule at the column exit. So wherever you see this mean value, mean concentration, so whatever the time that corresponds to the, when your concentration in the Gaussian peaks hits the maximum, so that will be your retention time. So your experimental outcome is always your Gaussian distribution. So everything under the curve, that should give some statistics about your concentration, which goes into the column chromatography at the inlet side of your column. So that should be equal to everything under the area under the curve. But whatever you have a mean value here, so you just draw the line, and whatever the time that you observe in the x-axis, that should be equal to your retention time. or if you want we can say the retention time TR is something that corresponds to the mean concentration. So whenever I mean mean concentration, you should know how the what's like how do you define a Gaussian distribution. Yeah, I just assume you all learned something about a Gaussian distribution or normal distribution. Both are same. So you have some value, something like that. So probably you know like even our if you look the grading of the students in any of the modules, at the end of the day if you plot them, say like student 1 get say like 10 marks, student 2 get 20, and so on. And if you plot them, say like if you starting from 0 to 100, class average will be somewhere around the mean value, which is 50 percentage, and some students will get near 100 percentage, some students will get near 0 to 5 percentage, something like that. And the whole class average will be roughly centered around the mean value, which is 50 percentage. And this is the same rule if you look the experimental outcome of the column chromatography. You have your experimental outcome will be always something like a Gaussian distribution, and then the entire area under the curve that will be equal to your concentration that goes into the reactor, something like grams per liter. Is area under the curve, I mean like it will be some number, that number should correspond to or should represent the concentration of your compound that enters your column, something like that. Yeah, I hope I didn't confuse you. And whatever the mean value that you have, so the time at which or the time when you observe the concentration in the column exit is equal to the mean value that should be equal to the or the mean concentration that should be equal to the retention time. It's very difficult to give some notations or give explanation for this type of experimental outcome. So this is something like when we say TR, at TR the concentration in the will be equal to something like an average, or we can call it as a mean concentration. So hope you all understand up to this point. If I didn't explain well, I'm so sorry for that. I worked with this. I work in the lab on high performance liquid chromatography almost every day. So it's, believe me, it's like it's easy to explain on a pen and paper, but it's very difficult to develop a method or even to interpret the data. Some people, they do a lot of mistake. So many people, they do some column chromatography experiment, and then they get some distribution like that, and then they always correlate the peak height, whatever I'm drawing here. Say like if this peak height, say some number, say 100, and this peak height say 120, and then they correlate these values 100, 120 with some concentration. Say at 100 corresponds to 50 grams per liter, 120 corresponds to 100 grams per liter, something like that. This is completely wrong. Yeah, so we have to take the area under the curve. So what we do is like we add something like 50 grams per liter, and then of analyte A, and then you get a distribution area under the curve. So let's say this area under the curve is equal to 100, and then we do another experiment. This time we inject something of concentration 100 grams per liter. You get a distribution area under the curve is say like 120. So we have to generate the standard plot in a way like 100, 120. In the y-axis should be equal to 50 and 100. So we plot something like that. So this is some basics that you should know about column chromatography. I know few students learned this technique probably during their co-op period. So for them, this will be really easy. If you are seeing this column chromatography for the first time, or if you are looking the experimental results for the first time in terms of like a distribution rather than some unique specific number, then you have to get some understanding what's a normal distribution is, what is that the mean concentration is all about, and what is the retention time, and so on. So if you have a distribution, the mean concentration, the time when you reach the mean concentration, that's we can call it as a retention time, TR. So that's the thing which is we covered so far. So this is the whatever this TR which I said, that's the retention time of your analyte. So how to calculate the retention time in the mobile phase? So this is the retention time of your analyte spent in the stationary phase. Stationary phase. And how to calculate the time spent by the analyte in the mobile phase? This is a very tricky one. So what we do in the lab normally, we take the column, and this time let's say we inject say 4, 5, say roughly there are 6 molecules of some reference analyte. Let's call it as RA. So this means reference analyte, and this analyte will never interact with silica, will not interact with silica. And then once you put your mobile phase, once you supply your mobile phase, it will carry your this analyte plug, which is nothing but some reference compound, and then you will get the same distribution at the end. So again, whatever the mean value, mean concentration, the corresponding time, the mean concentration in this distribution or in this Gaussian distribution curve, and then the corresponding time, that will be nothing but your Tm, or if you want the time spent by the, this should be the time spent by the analyte in the mobile phase. So what it says is like we know we have some analyte that will not interact with your solid particles, but so if that is the case, whatever the distribution that you observe here, that should be due to the, that should correspond to the time of this analyte spent only in the liquid phase, because nothing is getting adsorbed or dissolved, because they have practically no interactions with the stationary phase. So whatever the compound that goes through, and this the distribution that we observe, that's purely due to the time spent by the analyte in the mobile phase. So that's how we do in the lab. So normally what we do is like we will take a column, and then we will use some reference molecule. Sometimes we even call it as a tracer compound, and then we get the distribution. So this tracer material will not interact with your column, so from that one we will get some general idea about the time spent by the analyte in the mobile phase. And then so we know how to get the time spent by the analyte in the mobile phase. So and then we can do the experiment with our real analyte. Say this is analyte A, and then you supply your mobile phase. So and normally if you look at the how do you call, like we can inject A, and we can also inject our reference analyte, let's call it as R, at the same time. So both of them will travel through this column, and then let's assume we are going to we put some detector at the column exit, and if you look at the graph, the experimental outcome will look something like that. You have time in the x-axis, and then you have something that some number that we get from the detector. This can be some absorbance or any other value depending on what type of detector that we put at the end of the column. It can be a mass spectrophotometer, or it can be a simple UV spectrophotometer, and so on. Yeah? So, and again we will get some curve like this. So what is the first curve? This will be nothing but your reference molecule, or we can call it as a tracer compound. So this will not interact with your stationary phase, and this is something your analyte A. This is something your analyte A. So we know the mean value, which is your peak maximum. So the corresponding time should be equal to the retention time. So the time spent by your analyte in the stationary phase plus the time spent by the, how do you call it? So this TR should be the time spent by the analyte A in both stationary and the mobile phase, and we know what will be the times of from the peak of the first Gaussian distribution curve. So this Gaussian distribution corresponds to your how do you call it, like a tracer compound. So this compound will not interact with your stationary phase. So the peak maximum, so just draw the line towards the x-axis, the corresponding time, that should be the time spent by the tracer compound, or in the mobile phase. I hope you all understand up to this point. So if you want to calculate the time spent by your analyte only in the stationary phase, then you can even subtract this value. So we know retention time is like time spent by the analyte A in the stationary phase plus time spent by the analyte A in the mobile phase. So we know what is TR value. So, and we know what is TM. TM we calculate by using some reference material that will not interact with your stationary phase, but it will interact only with your mobile phase. Yeah, so that's why we need to add a reference compound in order to get this T suffix M value. That is a must. So I hope you all understand up to this point. I'm sorry for going a bit slow, but when you have an experimental outcome, so you should be able to interpret it. Yeah? So, and it's we always get some distribution, and you shouldn't be scared of this bell curve that you are going to observe. Whenever I'm going to throw you some chart, even in the final exam, I might give you some chart, and then I will tell, okay, look at the image. This is the experimental outcome that I got for some mixture of compounds. Can you tell me the retention time of compound A, compound B, and so on? And then if I ask you to calculate the retention time of compound A in the stationary phase or compound A in the mobile phase, tell to me. Then you have to think all these simple things. Like these are for this you don't even need to be a hardcore chemist. Yeah, all this just a common sense, and these are very simple analytical expressions. So let's go back to the topic. So if I ask you to calculate the time spent by analyte A in the stationary phase, it's very simple. TS TR minus TM. That's it. So so that's all, I think. So if I give in the exam something like a say this is for compound B, this is for compound A, this is your reference compound or a tracer, how do you call, like a tracer compound? or we can just call tracer. Yeah, and I will give some number, say like 6 minutes, say like 20, so 30 minutes. If I ask you to calculate the time spent by compound A in stationary phase and time spent by A in the mobile phase, and likewise if I ask you to calculate time spent by the compound B in the stationary phase and the time spent by compound B in the mobile phase, you have to calculate for me. And if I ask you to calculate the retention time, it's you have to calculate. Yeah, it's nothing there to calculate, it's already there on the graph. So your retention time of A is 20 minutes, don't forget the units, and retention time of B is 30 minutes. So the time spent by A in the stationary phase, that should be equal to, and then the time spent by both A and B in the mobile phase, that should be equal to 6 minutes. That should be equal to 6 minutes. So time spent by compound A in the stationary phase should be equal to 20 minus 3, and time spent by the compound B in the stationary phase, that should be equal to 30 minus 3. So these are very simple. 17 minutes, 27 minutes. So it's that simple. I hope you all get up to this point. And by the way, this TM value, the time spent by some of your analytes in the mobile phase, we call this as a dead time. This is another terminology, or some people they even call it as a hold up time. So the time that your column can hold your analyte molecules in the liquid phase. Yeah, so without just assume if your analytes are not interacting with your solid particles, but still what's the time your column can hold that analyte within that column. So that's why it's called as a hold up time, or the time spent by the your analyte in the mobile phase. Yeah, so this is very like if you have some analyte A and if you know that this is going to interact with the stationary phase, it's no way you can determine experimentally the time spent by this particular analyte in the mobile phase. That's why we need a second component, which we call it as a tracer compound. So only you need some compound that will not interact with your column material, packing material. Only then you can calculate your dead time, and the dead time that you calculate with this tracer compound, we assume that's the time that will be spent by all of your analytes in the column. Yeah, say like if you start your column with A plus B plus C plus D, let's say our mixture contains 4 compounds, and we are going to and just assume all of these 4 compounds or molecules, they are going to interact with your packing material in the column. If that is the case, we cannot obviously determine what's the time, how much time each of this compound will spend in the mobile phase. So to do that, we need some additional compound, something like a tracer compound. So that shouldn't, this particular tracer or this particular analyte will not interact with your stationary phase, and then only with this type we need the retention. We calculate how do you call we calculate how much or what's the time spent by this tracer material inside the column, and we assume if that the mean value, say it at 6 minutes, so that will, we have to assume that will be the time spent by all the other analytes in the mobile phase. So I hope you all understand up to up to this point. So dead time in the sense something like the time spent by your analyte molecules inside the column, provided or for the condition that these analytes are not interacting with your stationary stationary phase. Oh my god. This is such a complex topic for me to explain. Yeah, I think we did some experiment. We learned something about retention time and also the time spent by your analytes in the stationary phase and the mobile phase. And now we can define some quantity which we call it as a retention factor. Retention factor, let's call it. This is a very important parameter. In the exam, I might give you some chart like a some experimental outcome. I might take it from some literature and then I will ask you to calculate the retention factor for me. So what is this retention factor is all about? So this is a simple analytical expression. This is small k. So we already used a capital K to represent equilibrium concentration. Concentration of stationary phase divided by concentration of your analyte in the mobile phase. You all remember that. So retention factor, this is a small k. This will be equal to retention time of your analyte minus the retention time of your analyte in the mobile phase divided by retention time of your analyte in the mobile phase. So this is nothing but the time spent by your analyte in the stationary phase, Ts by Tm. So why do we need this value? Yeah, so we can calculate. We know how to get TR, we know how to get TM, we know how to get TS as well. So why do we need this factor? Why do we take a ratio TS by TM? And that's because every lab have different type of column. Yeah, this column length will vary. Sometime we can buy 15 centimeter column, sometime we can buy 5 centimeter column. So just assume that we have a 5 centimeter column and then we have a 15 centimeter column, and the packing material whatever we have in both of these column is exactly the same. Yeah, we fill the same type of silica particle with same bead size, same level of porosity, same level of surface area. So practically we take the same silica material and we put it in these two columns. So these two columns have same material. The only difference is the column length. So if we do some experiment, say like we put some analyte A plus B and say analyte A plus B. Okay, this, let's put a 10 centimeter column. That will be easier to explain for me. So you supply your mobile phase, so and then you take your experimental outcome and you will get some distribution at the exit, say like a column A, sorry, for compound A and distribution for compound B. So this one happened at 5 minutes for compound A and compound B elutes at something around say 20 minutes for example. This is for compound B. And if you perform the same experiment in 10 centimeter column, this is the experimental outcome will look something like that. So say time in minutes and then some number in the y-axis. This can be your absorbance if you are using some detector or so on, depending on the type of detector we have. So just assume some number that can be correlated to your concentration. So this time it will happen, your compound A will elute. You will have one distribution curve, one Gaussian distribution, another Gaussian distribution. So even this one should be like a Gaussian distribution, not like a triangle. Yeah, so this time your compound A will elute at 10 minutes and here your compound B will elute at 40 minutes, because the size of your column is exactly twice in the second experiment. So let's call this is as a TR value and this is your TR, retention time of A, retention time of B, and here retention time of A, comma retention time of B. And then let's assume your we also inject our tracer compound, and that elutes say when TR is equal to 1 minute, and here the tracer compound will elute at 2 minutes because the column size is exactly twice. So why do we have a retention factor? Is like retention time of A, retention time of B, retention time of A, retention time of B. So if you calculate the retention factor for the column 1, K1, K will be equal to, let's calculate the retention factor for compound A. So that will be TR minus TM minus TM divided by TM. So that will be equal to 5 minus 1 divided by 1. That should be equal to 5 minus 1, 4 divided by 1. That should be equal to 4. And then if you calculate the retention factor for compound B in the column 1, so this is for 5 centimeter column. So that should be equal to, I'm just solving this because these are the type of problems that you are going to expect in the final exam, probably like an objective type question. So TR minus TM divided by TM. So this will be equal to 20 minus 1 divided by 1. So that will be equal to 19 minutes, something like 19, sorry, there is no units. So you have time units in the numerator, time units in the denominator, so both will get cancelled. So your retention factor will be 4, retention factor will be 19. So, and then if you do the same experiment with the column 2, which is the 10 centimeter column, you calculate the retention factor. Say, what is your TR value this time? 10 minus 2 divided by TM is 2. So that should be 8 divided by 2. That's equal to 4. This is for retention factor for A in column 2. The length of this column is 10 centimeter now. And then we calculate the retention factor for compound B. That should be equal to 40 minus 2 divided by 2. That should be equal to 38 by 2. That should be equal to 19. So what we observe from this one, so the retention factor becomes how do you call it, something like normalizes your results. So something like it nullifies the effect of the column length. So imagine it's like if in my lab I have a column of 5 centimeter, and in your lab or some other industries they have a column of 10 or even 20 centimeters, and let's assume we both bought the same column with same type of packing material. The only difference we have is the column length, and it's okay, like how do you call, like it's a matter of choice whether to use a very long column or a shorter column. Once you have the expertise in this area, you will know which type of column to buy. But for the moment, let's assume we have two different columns. I am using a smaller column and you are using a longer column, and we both of our intention is to separate A and B using this chromatographic technique. And we assume we both are dealing with the same type of material, silicon material, so we both purchased the silica column. And if I say to you the retention factor in my column, say I am using a 10 centimeter column, and the retention factor of my compound A is something around is 4, and the retention factor of compound B in my column is 19. And if I give you my column length 10 centimeter, and if I have a column in my lab at 5 centimeter, I can easily calculate what will be the retention time in the smaller column, say 5 centimeter column. So what you can see, like if you see 5 centimeter, the retention factor of A is 4 and the retention factor of B is 19, and then it's the same there in the if you use a longer column, the retention factor of A is 4 and the retention factor of B is 19. So that's the key advantage of expressing the results in terms of retention factor, we can stop, like we can do the experiment and we know how to calculate TR, TM and TS, T suffix S and so on, but it's better to calculate a few more parameters, so that will be like a more generalized value. If you use a retention factor, that is a that will be more meaningful, because most of the labs, everyone have a we use different column length, so retention factor is a better way to present your results. So if you want, we can even write it in a bit mathematical way, just to say, like in the first lab we have some column 5 centimeter, second lab we have say 10 centimeter, so the retention time will be exactly twice, so T will be equal to, our retention time will be exactly twice in the longer column. The smaller column K will be equal to TR minus TM divided by TM. So in the longer column, TR will be twice, TM will be twice. So our retention factor of any particular analyte will be 2TR, 2TM divided by 2TM. So that will be equal to, you take 2 common factor outside, TR minus TM divided by 2 multiplied by T suffix M, 2 get cancelled. So this will be equal to your retention factor in the small column. So that's the main advantage of expressing the results in terms of retention factor. And another reason, we have one more good reason to express the results in terms of retention factor. So the first reason is like it normalizes your experimental data, and then so especially if you are dealing with the different column length, so that's the so normalize in the sense, like it normalizes the operating conditions that should vary between column to column, especially if the length of the column is different. I hope I managed to explain this well. We have one more reason to express the results in terms of retention factor, because your retention factor can be related to your equilibrium constant, or we can call this even as a separation factor. So separation factor, or we can call it as a distribution constant, or distribution constant. This is nothing but the ratio of your analyte in the stationary phase and the ratio of the analyte in your mobile phase. So how to find the relationship that exists between your retention factor small k and your distribution constant or your separation factor k. So we all know k is the guy who dictates the retention time and also the degree of separation. So we will come back to the efficiency of the column and the resolution of the separation, or if you want we can call it as the degree of separation later. But for the moment, let's try to connect these two values, k and small k and capital K, which is nothing but your retention factor versus your distribution constant. So we have to derive this expression, we have to go back to our first expression, where we know our retention time is sum of the time spent by the analyte in the stationary phase and the mobile phase. So Ts will be equal to Tr minus Tm. So and then we know K is equal to Ts by Tm. We already calculated before. And now where is the page number? Is here. I already calculated this one. K is equal to Ts divided by T suffix em. So what it says is like it already, if you look at this ratio, so Ts is something like let's say we put paracetamol in the at the inlet of your column. So let's say this is the Ts corresponds to the time spent by your analyte or paracetamol inside the column, and Tm will be the something like the time spent by the analyte in the mobile phase. So that itself already talks a bit about your K value. We already know the capital K, which is nothing but your distribution coefficient, Cs by Cm. So what does this mean? Like, so the longer the time you are analyte, so longer the time spent by the analyte in the stationary phase, so it means the K value is going to be higher. Yeah. And this K value will be low if the time spent by the analyte in the stationary phase is less. So that gives you a bit of some connection between your distribution constant and your retention time. So now you have to think a bit. So we know what's K, capital K, what is small k. So at any instant of time, say like say at particular time t, so if you calculate the number of molecules spent by your analyte A, so sorry, the number of number of molecules of analyte in the stationary phase, say ns, and say the number of molecules at that particular instant of time in the mobile phase, let's call it as nm. If you take that ratio K Ts by Tm, that will be roughly equal to this ratio of number of molecules of your analyte in the stationary phase and the number of molecules of your analyte in the mobile phase. This ratio will be exactly equal. The time spent by your stationary phase and divided by the time spent by the analyte in the stationary phase and the time spent by the analyte in the mobile phase, that will be exactly equal to, at any instant of time, whatever the time it can be, this ratio will be equal to the number of molecules of analyte A in the stationary phase divided by the number of molecules in the mobile phase, because these both are directly correlated. So what does this mean? Like, if the number of molecules in the stationary phase is going to be higher, which means the time spent by that particular analyte in the stationary phase, it's going to be higher. So they are proportional to each other. So that's why this ratio gets equaled. So K is equal to Ts by Tm. That should be equal to number of molecules of S divided by number of molecules of A in the stationary phase divided by number of molecules of A, or if you want you can call it as analyte, in the mobile phase. I can write it here. Number of molecules of analyte in the stationary phase divided by number of molecules of analyte in the mobile phase. In the mobile phase at any instant of time, at any particular time. Yes, let's say like we are measuring this ratio, like some discrete time interval, or say like at 2 minutes I started the experiment, and now I'm going to check my concentration of my analyte in the stationary phase and the concentration of my analyte in the mobile phase within the column, and that ratio should be equal to Ts by Tm. So if you want, we can even, instead of expressing in terms of number of molecules, so I can say, let's use capital N here. K is equal to Ts by Tm, that's equal to capital Ns divided by capital Nm. So capital N refers to the number of molecules. So if you want, we can express in terms of moles. So K is, let's say, Ts divided by Nm. So this time small n refers to the moles of analyte in the stationary phase. We already solved a few problems while during this lecture. You are going to expect something similar in your final exam. So moles of analyte in the mobile phase. So in the exam, I might even give this retention factor, say like K, and then I will give the chart that we normally observe in a longer column, or I will just give some spectra like that, chromatogram, something like that. So I will clearly mention the time and so on, and then I will tell the column length is equal to 20 centimeter, and then I will tell I need to perform the same experiment in a column of 40 centimeter, or maybe a column of 5 centimeter. So you have to tell to me what will be the retention time of this particular compound. Say this is A, this is B, this is your tracer molecule. So you have to tell to me what's the TR, TM, TS in both of these columns, 40 centimeter and 5 centimeter. So you have to calculate it. So if you want, I will draw some diagram, so it's not a big deal. So you have to try to solve it by yourself in the home based on whatever I taught you in this lecture. In the exam, I will make a better nice drawing. This is awful. So this is your tracer or let's put TM for this is TRA, TRB. Let's say the column length is 40 centimeter. Say this is side 2 minutes, and here the time is equal to say 10 minutes, and say retention time of B, say like 30 minutes. So try to calculate the TR, TS, TM for A, B in the column of length. What can we put? Say 5 centimeter, 10 centimeter, 20 centimeter, and 30 centimeter. So try to practice in the home. So you all know what's the formula to use. K is equal to TS by Tm. This is nothing but Tr minus Tm divided by Tm. So using this formula, try to get all this, solve this problem. Yeah? That will be a nice homework for you to do, and you are going to get this type of problem in the final exam. Okay, I wouldn't promise that you are going to get, but you might get. So let's come back to this topic. So now we are trying to relate our retention factor with our distribution constant K value. So let's give this equation, say let's call it as equation 2. So K is equal to Ts by Tm, that's equal to Ns by Nm. So what we are going to do is like this is going to be very tricky. Let's just divide this value. So let's say the volume of stationary phase volume of stationary phase, let's give some notation Vs, and then volume of mobile phase, let's give them some notation, let's call it as Vm. So volume of mobile phase. So we are doing these things just to find the relation that exists between your retention factor and your equilibrium constant. So what we are going to do is like we take equation 2 Ts by Tm, and then on the numerator side you just multiply and divide by Vs by Vs, and divided by and in the denominator side you just multiply by Vm by Vm. So obviously we can cancel these two, but we are doing this to make some things a bit simpler, to make the things a bit more easy. What to do with this one? So what is this? So we all know like the number of, if we take a solution, so the number of moles, say like number of moles of A per unit volume, that's nothing but our concentration. So what does this mean? So we can rewrite this expression, Ns by Vs multiplied by Vs divided by N suffix m divided by V suffix m multiplied by Vm. So this will be equal to, so just follow the pen. So this is nothing but concentration of your solute in the stationary phase multiplied by Vs. This is nothing but your concentration of solute in the mobile phase, Cm multiplied by Vm. So what is this? This the ratio. This is nothing but your equilibrium constant K, or distribution coefficient, distribution constant, capital K. So K will be equal to something like a capital K multiplied by Vs divided by Vm. So this is like volume of your stationary phase, this is your volume of your mobile phase. So some people, they call this how do you call, we can give a notation, let's beta is equal to Vm by Vs. So let's call this as equation 3, this as equation 4. So where equation 3 will, if we substitute equation 4 in equation 3, we will get K will be equal to capital K multiplied by, sorry, divided by beta. So how do you write capital K multiplied by Vm by beta? Yeah, this is beta, that's correct. So your retention factor will be equal to your distribution constant divided by beta value. If you don't have this COVID, we can really go to the lab, we can do a HPLC experiment, and in fact I did a small experiment for you using a thin layer chromatography. I don't know if the time allows, I can try to compile into a small PowerPoint presentation, and then I will show you some how the whatever the terminologies that we learned now, like retention factor, and how fast your mobile phase moves, how fast your stationary phase moves. That's something that we can observe even in even using a small simple experiment in the lab. I can try to show you if I have time, and I don't want to stress you more, especially we are almost nearing the final week of this semester, so I want to finish this module in the right time, so you will also have enough time to read whatever that we are learning at the moment. I hope you all are fine up to this point. So we know what's the retention factor. Now we also learned what's equilibrium constant. We know the time, different type of time and the units for them. And now we related the retention factor with the distribution coefficient and so on. this beta value we call this beta, which is nothing but volume of mobile phase divided by, sometimes we call it as a phase ratio. Volume of phase ratio, what is that? Is like some in something like the volume in the mobile phase and the volume of your stationary phase. So that's the purpose. I will save this video before my tab crash.